Welcome to Ready to Derive. Up until this point in calculus, we have worked solely with functions. Recall that a function passes the vertical line test, meaning that for every x value, there is only one y. Not all curves, though, behave like this. So some curves, for example, the one defined by this equation, are better known as relations. So while all functions are relations, not all relations are functions. Now, why is this a very cool curve to analyze? Because if you graph it, I went to desmos.com to graph this, you will get this beautiful graph. Because you can't isolate y in terms of x for these type of relations, you need to know the methods of implicit differentiation. So if you want to have some fun, go on to desmos.com and type in any combination of x and y you like and be prepared to be amazed. If we look a little closer into one of the little islands, we see some really interesting features. We feel places where the tangent line is horizontal, where it's vertical, and you can actually find the slope of any point on this curve by knowing the method of implicit differentiation. So without further ado, let's get started. So let's start by understanding the difference between an explicit and implicit equation. So here is an explicit equation, one in which y is isolated. And basically all functions fall under the umbrella of explicit equations. Now, before we find the derivative, as we've done in the past, I'd like you to come at it a slightly different way. So think of any equation. We know that we can always do whatever we like to both sides. So I could take the square root of both sides, because square root, taking the square root, is an operator. I could also take the sine of both sides. The sine is an operator, or the log, etc., etc. So I would like you now to think of the derivative as an operator, as we've talked about before, and we are going to take the derivative of both sides. Now, the left-hand side, d by dx of y, we know that we have just been calling that dy by dx, right? Because that's the symbolism for the derivative of y with respect to x. And on the right-hand side, we might like to first write this as 5x to the minus 3, and then we can use the power rule, and that will be negative 15x to the minus 4, or negative 15 over x to the 4. Now I'm going to rewrite this same equation as an implicit equation. Notice the only thing that I've done is multiplied x cubed to both sides, and y is no longer isolated. Now let's do the same thing. Let's take the derivative of both sides with respect to x. Now you have to be careful here, because we have a situation where we've created a product of two functions. Let's call this u, so u is x cubed, and v is y. Now we know that y is dependent on x, so therefore it is a function of x. We've just rearranged it. So since we have a product, we're going to have to use the product rule. And we know that, okay, so u, the derivative of u is 3x squared times y plus u, which is x cubed, times the derivative of v. Now the derivative of v is just, we just figured it out before, it's just dy by dx, because we can't really do anything, so we just leave it as the symbol that represents it. And the derivative of the right-hand side is 0. Now, let's tidy this up a little. Let's get dy by dx alone. So we would subtract 3x squared y. Then we would divide by x cubed. Now dividing by x cubed, let me just do that in a different color. Dividing by x cubed, notice that the x is going to cancel out when left with negative 3y over x. Now, wow, that doesn't look like this answer here just yet. But if we remember what y is in the first place, well, what was y in the first place? It is 5 over x cubed. Then we can make a replacement of 5 over x cubed over x, and that ends up being negative 15 over x to the 4th. Wow, that was a lot of work to prove the same result, which on the explicit side, which was much easier to find. So why would we bother going through all that work to find the derivative? And the reason is because there are some equations which cannot be expressed as explicit ones, and can only be analyzed as implicit. So let's look at some other equations and sort of decide if explicit is the way to go or implicit. So this is a linear equation, and y here is easily isolated. So of course you'd want to take the derivative written as an explicit equation. But here, x squared plus y squared equals 3. That's the equation of a circle. And while you can isolate y, if you try this yourself, you would get this. You would get the equation of the two semicircles that make the circle up. That's a little harder to take the derivative of, and keeping an implicit form would make more sense. Now, here's one where it would be really hard to isolate y, and we have no choice but to tackle it using implicit differentiation. E to the y equals x minus 1. Well, we could rewrite that as y equals ln x minus 1. So that's probably, and that is probably the more convenient way to take the derivative. But that is going to be very hard to isolate y in. Let's take another one, sine of y equals x plus 1. Technically, you could take the inverse sine of x plus 1, but you would lose some solutions by doing that because you would restrict the values that y could take on. And then finally, this is a relation we're going to analyze later in this video. This would be impossible to isolate y in. So we're going to do a little warm-up exercise so that we are better able to find the derivative of expressions involving y. Let's have a look. So d by dx of the square root of x. We know the shortcut for that, if you've watched my previous videos, is 1 over 2 rad x. If you're not clear on that, we'll rewrite rad x as x to the half, take the derivative, and put it back in rad form, and you'll get the same answer. So by the chain rule, this will be 1 over 2 rad sine x times the derivative of the inner function, which is cosine x. Let's make it a little more complicated in there. So that will be 1 over 2 rad e to the x plus ln x times the derivative of the inner function, which is e to the x plus 1 over x. So now, what if I have a mystery function in that radical? Well, by the same reasoning, we know that it would be 1 over 2, whatever that is. And by the chain rule, we know that we would have to find the derivative of that inner function. Well, following that reasoning, what should we do here if that inner function is y? We know that y is related to x, so we know that we can find its derivative. It's not a constant, so we would put 1 over 2 root y times the derivative of the inner function, which is just dy by dx. So we saw clearly in the last slide that the chain rule is what is going to be able to enable us to carry out implicit differentiation. So let's kind of summarize this. So if we want the derivative of some function of y, in the last slide it was the square root of y, we find the derivative of the outer function, right, f prime, and then we multiply by the derivative of the inner being y. So since we can't actually do anything with it, we just leave it as dy by dx. Let's take a couple of examples. So the derivative of e to the y will be e to the y times the derivative of the inner function, which is just y. So we just have to write dy by dx because there's nothing we can do. And what about 3y to the fourth? That will be 12y cubed, the derivative of the outer function, times the inner. Well, once again, it's just dy by dx. We're starting to see a pattern here. The derivative of tan y will be secant squared y times dy by dx. So we see that we keep materializing dy by dx, and this is going to be the secret to finding dy by dx in equations where y cannot be isolated. So let's have a little practice finding dy by dx by implicit differentiation. So here's a relation. And we're going to remember d by dx is an operator, so we'll take d by dx of both sides, the derivative of both sides, and I'm actually going to split up the terms so we can take one term at a time. So the derivative with respect to x of y squared is going to be, so the derivative of squaring is 2 times that quantity times the derivative of y with respect to x minus by the same reasoning, the derivative of 2 times something is just 2, because that's a constant. And then there's no y remaining, right? So because the derivative of 2y is 2, and then we multiply by the derivative of y with respect to x. And the right-hand side we should be much more comfortable with. That's 9x squared. Now, to get dy by dx, we actually have to isolate it, and the only way we can do that is to factor it out of these two terms. So we get 2y minus 2 times dy by dx equals 9x squared, and then we can divide through by 2y minus 2, and we get 9x squared, and while I'm at it, I might just factor out the 2. And that's our, here we found a formula for the derivative by implicit differentiation. All right, so here is another example, one that we saw before, where it would be very hard to isolate y. Take the derivative of both sides with respect to x. Now, I almost think that the right-hand side is easier to do, so I'll start with that. So d by dx of x is just 1, and d by dx of y, well, that's just dy by dx. Can't do that, don't know what y is, so leave it like that. Now the left-hand side, the derivative of e to anything is e to that same quantity times the derivative of the inside. Now the derivative of xy, we have to be careful. So we have a product, so x is u, y is v, and we need to take the derivative of x, which is 1, times y plus x times the derivative of y, which is dy by dx. Now we have a little problem because we have dy by dx on both sides of the equation. So what we have to do here is get it to one side. So we need to distribute first. We're going to, so we can write this as y e to the xy plus x e to the xy times dy by dx equals 1 minus dy by dx. Now let's switch sides. Let's get all the dy by dx terms to one side and the others to the other side. So I'm going to keep this one here, and I'm going to bring this dy by dx over, so it becomes plus dy by dx. And then I'm going to bring this term, which doesn't have a dy by dx, to the other side. So we get this. And then we factor out dy by dx. Now, rather than write it factored on that side, I'm just going to bring it to the other side. So we get 1 minus y e to the xy. And if I was to factor out the left side, I would get x e to the xy, and don't forget that plus 1. And that very convoluted expression or equation is dy by dx. Notice that in both cases, dy by dx is expressed in terms of x and y, right? So don't be surprised that it's not just in terms of x. That's what implicit differentiation will look like. And let's see why this is important. So let's bring up the relation from the previous slide and the formula for dy by dx that we found by implicit differentiation, and see in ways in which this could be useful. If we look at a graph of the relation on Desmos, it's pretty cool. And we realize that we can use dy by dx to answer some questions about this relation. So for example, we can find the slope of the curve at 1, 3, which is a point it passes through. So 1, 3, thinking the slope looks it's about 2, let's see what we get. So what we're really asking is, what is the value of dy by dx when x is 1 and y is 3? And that's how we write that. All right, so all we have to do, and now we have the formulas, we just have to plug in. So that's 9, x is 1, 9 times 1 squared over 2, y is 3, 3 minus 1 is 9/4, which is 2.25, which is very close to what we estimated the slope to be, around 2. We can also find the location of any horizontal tangent lines, and that is going to happen whenever dy by dx equals 0, which happens only when the numerator is equal to 0. So what does that look like? That means we will set 9x squared equal to 0, which only happens at x equals 0. So if we look over there, it does look like when x is 0, we have a horizontal tangent line there. We actually have 2 of them. So how do we find the y coordinates of those? Well, I know you can read them from the graph, but you should get into the habit of using the equation. Okay, so here's the original equation between relating x and y, and all we have to do is plug in x equals 0 into that. So we get y squared minus 2y equals 0, y times y minus 2 equals 0. So y equals 0 and y equals 2 are the two y coordinates that go with x equals 0, and then we can go, so we see here at 0, 2 is one horizontal tangent line, and 0, 0 is the other. What else can we do with this magic formula? We can find the location of any vertical tangent lines. That will happen when dy by dx is undefined, which will only happen when the denominator equals 0. So we set the denominator equal to 0. That's 2y minus 1 equals 0. And that's when y equals 1. So when y equals 1, seems like we have a vertical tangent line. It's true. Now that x coordinate is hard to find, so we really have to use the equation here. So to find x, we plug in y equals 1. We get 1 minus 2 equals 3x cubed. If we isolate x, we'll get the cube root of negative 1/3, which is approximately negative 0.693. So we found the coordinate of this vertical tangent line to be negative 0.693, 1. So we'll end with one more problem, finding the equation of the tangent line to the curve I'm about to reveal. And isn't that gorgeous, right? The equation of that relation is y sine of 2x equals x cosine of 2y, one that would be impossible to isolate y in, so we've got to use implicit differentiation. And to find the equation of the tangent line, we need to find dy by dx first and then evaluate it at that point. So I'm going to take the derivative of both sides. Notice that I've kind of put a multiplication sign in there so that you realize that it's the product of two functions. So we have to, or y is technically not a function, but the product of two quantities that both depend on x, so we have to use the product rule. So the derivative of y with respect to x, dy by dx, times sine of 2x plus y times the derivative of sine 2x. And we know that that's cosine 2x times 2. Now for the right-hand side, so now u is x, and this quantity is v. So the derivative of x is 1 times the cosine of 2y, and then we're going to have plus x. Now be careful here, the derivative of cosine 2y, we have kind of a triple chain rule here, or maybe it's double to be precise. But anyway, so the derivative of cosine is negative sine of that quantity. But we also have to multiply by 2, because that's the derivative of 2y, but the derivative of y also is dy by dx. So watch out you don't lose that. Let's tidy this up a little bit. So sine 2x dy by dx plus 2y cosine 2x equals cosine 2y. And then we have here minus 2x sine 2y dy by dx. Let's get those dy by dx terms onto one side. So sine 2x dy by dx, and we'll bring this one here to the other side. So it becomes plus 2x sine 2y dy by dx. And we'll bring, and then so cosine 2y stays on the right, and we're going to bring this over. So it becomes minus 2y cosine 2x. We are going to factor out dy by dx from these two expressions and set that equal, then divide by that quantity to save a little time. This is what you should get. And now we're going to take this formula for dy by dx and work with it to find the equation of the tangent line. So just to end here, here's the equation of the relation. Here's the beautiful graph. Here's the results of our hard work on the previous slide, getting the derivative. And remember, we're trying to find the equation of the tangent line at the point pi over 2 comma pi over 4. So the first thing we need to do is plug in those values of x and y. So I've taken the liberty of just putting that in, and we can see we've got some simplifying that we can do. This is going to be pi over 2. This is going to cancel out to 2 here. These are going to cancel here as well. Gosh, this is fun. And then that's going to become a 2. So we are going to be left with this. And cosine of pi over 2, well, cosine of 90 is 0. Cosine of pi is -1. Sine of pi is 0. And sine of pi over 2 is 1. And that is going to reduce to pi over 2 over pi, which gives us 1/2. So that is the slope of the tangent line. So therefore the equation of the tangent line will be y minus pi over 4, that's the y coordinate, y1, equals 1/2 times x minus pi over 2. And then if we zoom in on this graph to that location, we see the equation of the tangent line that I typed into Desmos fits perfectly. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.